Here is the combined summary. MSP-MVS is a novel multi-view stereo method that targets the reconstruction of textureless areas, which traditional MVS methods struggle to accurately reconstruct due to the lack of reliable pixel correspondences. The proposed method employs multi-granularity segmentation prior guided patch deformation, leveraging the recently proposed semantic SAM segmentation to extract multi-granularity depth edges. These edges are integrated as a prior to restrict patch deformation within homogeneous areas, reducing the potential for reconstruction failure. The method first extracts multi-granularity depth edges using semantic SAM segmentation and then integrates them as a prior to guide patch deformation. An anchor equidistribution strategy is introduced to equip patches with more uniformly distributed anchors, ensuring comprehensive coverage of their own homogeneous areas. However, the increased number of anchors raises computational loads and reduces time efficiency. To address this, iterative local search optimization is proposed to represent larger patches with sparse representative candidates, significantly enhancing the expressive capacity of each patch. The pipeline begins with multi-granularity segmentation using semantic SAM, generating 3 masks of varying granularities from coarse to fine. These masks are used to derive boundary maps that capture semantic information at different levels: scene, instance, and feature. The aggregated segmentation map is obtained by retaining reliable masks that maximize the quantity of optimal distribution among internal pixels, serving as a new constraint to form a new anchor collection for patch deformation. An edge correction strategy based on the conditional random field algorithm is developed to address issues such as edge blurring and overlapping in panoramic segmentation. The CRF model consists of unary and pairwise potentials, incorporating both geometric and color similarities to refine the edge correction process. The deformable patch matching cost is calculated as a weighted sum of the cost within the patch and the cost of the deformed patch, ensuring anchors are within homogeneous areas by classifying them into different subsets based on their intersection with boundary maps. This paper presents a novel approach to multi-view stereo (MVS) depth estimation, focusing on improving the accuracy and efficiency of the patch matching process. The proposed method, MSP-MVS, introduces 2 key innovations: anchor equidistribution and iterative local search optimization. Anchor equidistribution ensures a balanced division of regions without wastage by selecting multiple anchors per sector, avoiding memory inefficiency and enhancing the reliability of anchor selection. Iterative local search optimization identifies sparse reliable candidates to represent each anchor patch, effectively broadening their receptive field. The optimization process involves categorizing candidates into 3 types based on their characteristics and uses an ILS function to minimize cost and maximum variance of profile. The MSP-MVS method is evaluated on the ETH3D and Tanks Temples benchmarks, outperforming learning-based methods such as PatchMatchNet, ITER-MVSLS, MVSTER, EPP-MVSNet, EPNet, and traditional methods like PCF-MVS, ACMM, and ACMMP. Quantitative results show that MSP-MVS achieves the highest F1 and completeness scores on both datasets, demonstrating its effectiveness in enhancing the accuracy and efficiency of MVS depth estimation. MSP-MVS leverages multi-granularity segmentation prior to constraint patch deformation within homogeneous areas, using semantic SAM for extracting multi-granularity depth edges. These edges are then aggregated and corrected for accurate patch deformation. Ablation studies on the ETH3D benchmark validate each proposed component's effectiveness, indicating that all components contribute significantly to the overall method. Future work includes leveraging semantic SAM to extract various 3D instances from point clouds, facilitating object-level scene editing and improving scene interactivity. The method achieves comparative runtime compared to SOTA methods like APD-MVS and HPM-MVS, demonstrating its superior performance and strong generalization capability. In the realm of multi-view stereo, MVS, and autonomous driving, numerous research efforts have been dedicated to enhancing the accuracy and efficiency of depth estimation from various viewpoints. The paper by Wei et al. 2023 introduces surround OCC, a novel approach for predicting 3D occupancy in autonomous driving scenarios using multi-camera setups. It leverages geometric constraints and photometric cues to achieve state-of-the-art results on the KITTI dataset. Similarly, Wei et al. 2021 propose RMVS-Net, which adapts to different scenes through adaptive aggregation and recurrent refinement. This model significantly improves depth estimation accuracy in diverse environments. Xu et al. 2022 focus on geometric consistency and planar prior assistance in MVS, demonstrating improved performance over previous methods. Their work builds upon earlier research, Xu and Dao 2019, that emphasized the importance of multi-scale geometric consistency for enhancing MVS accuracy. Zhang et al. 2023 revisit the representation of MVS-Net, introducing a region-aware approach that better handles textureless regions and improves overall depth estimation. Meanwhile, Zhang et al. 2023 introduced Geo-MVS-Net, a geometry perception-based MVS method that outperforms existing techniques on various benchmarks. Other notable contributions include the work of Yuan et al. 2020, who developed dense hybrid recurrent multiview stereo net with dynamic consistency checking, and Yao et al. 2018-2020, who introduced MVS-Net and its large-scale dataset blended MVS for generalized MVS networks. Yu and Gao, 2020, proposed fast MVS-Net, which utilizes sparse-to-dense propagation and Gauss-Newton refinement for efficient and accurate depth estimation. Furthermore, Yuan et al. 2024a, 2024b, explore segmentation-driven deformation MVS with spherical refinement and M-optimization, as well as textureless-aware segmentation and correlative refinement-guided MVS. These approaches aim to address challenges such as textureless regions and varying lighting conditions. Lastly, Zhu et al. 2023 discuss the use of embedded conditional random fields for semantic segmentation, aiming to mitigate class weight confusion caused by boundary effects. Zhu et al. 2021 also reviewed 3D printed multifunctional materials enabled by AI-assisted fabrication technologies, highlighting the potential for such innovations in various fields. In conclusion, these papers collectively contribute to the advancement of MVS techniques, addressing various challenges and limitations in the field. They demonstrate the importance of geometric consistency, adaptive aggregation, region awareness, and geometry perception in enhancing the accuracy and efficiency of depth estimation from multiple viewpoints.